When you see a robot whirring around, it's easy to get fixated on the cool hardware, the gears, the motors, the shiny metal. But the real magic, the invisible genius that makes it all work, often starts with just a single line of code. Today, we're going to pull back the curtain and really unpack the software that brings these machines to life. Okay, so take a look at this. Robot.navigate, destination. It looks so clean, right? So simple. If you've ever written any code, this feels nice and familiar. But what does it actually take to make this one little line do anything in the real world? Well, beneath this elegant surface, there is an absolutely mind-boggling amount of complexity. And that right there, that's the billion-dollar question, isn't it? How can an abstract digital instruction actually command a physical machine in our messy, unpredictable world? The answer is this constant looping journey. The robot has to sense its environment, plan its next move, and then, finally, act on that plan. Let's break that loop down piece by piece. So where do we even begin? Well, it all starts with perception. Before a robot can do literally anything, it has to understand what's going on around it. And that's not just about slapping some sensors on it. It's about the software that translates a fire hose of raw data into actual useful meaning. You see, a sensor on its own just spits out raw numbers, a stream of voltages, a bunch of pixel values. By itself, that's totally meaningless. The sensing software is the translator. It takes all that noisy, low-level data and turns it into information a program can actually use. So a specific voltage from an optical sensor becomes, aha, the coffee pot is empty. A flickering light value becomes, uh-oh, my computer just crashed. This is the first absolutely critical step, grounding the software in reality. Okay, so the robot has a meaningful picture of its world. What's next? Well, it needs a plan. This is where the robot's digital brain kicks in and starts calculating the best possible way to get from here to its goal. Let's use a classic example, a mobile robot that needs to get across a room. First, the goal is defined. Get to that target. Then the software uses its map of the world to identify every single obstacle: walls, chairs, people. It then runs through literally countless possible routes, instantly throwing out any that end in a crash. Finally, it calculates the one optimal path, the absolute shortest and safest route. And all of this happens in a tiny fraction of a second, before a single wheel even thinks about turning. All right, so our robot has its senses, it's got a plan, but now comes the hard part, the really hard part, actually moving. This is the moment where that perfect, clean digital plan has to slam into the messy, unforgiving laws of physics. The software can't just know the path, it has to figure out exactly how to command the motors to follow it. And the first piece of that puzzle is something called kinematics. The easiest way to think about this is like the robot's skeleton. Kinematics is the pure geometry of movement. It's all about the positions, the angles, the connections between the joints. It describes all the ways the robot could possibly move, without worrying about things like weight or gravity. Just yet. Now, kinematics kind of has two sides to it. You've got forward kinematics, which, honestly, it's the easy part. If I tell you the angle of every single joint in a robot's arm, you can calculate exactly where its hand is. Simple enough. But then there's inverse kinematics. This is the reverse, and that, my friends, is way, way harder. The robot knows where it wants its hand to be, and the software has to solve for the exact angle of every single joint to get it there. For a complex robot, there might be dozens of correct answers, or sometimes no answer at all. So if kinematics is the skeleton, then dynamics, that's the muscle. Once we know the joint angles we need, dynamics answers the next big question. How much oomph, how much torque do you need from the motors to actually make that move happen? This is where the software has to wrestle with the real world. The mass of the arm, the weight of whatever it's holding, friction, inertia, gravity, the whole shebang. It's the physics that turns a geometric idea into a physical action. So you're probably thinking, wow, that's a lot. And you're right. Trying to manage all of that, the sensing, the planning, the kinematics, the dynamics, from scratch every single time, for every new robot, it would be basically impossible. Thankfully, developers today don't have to. They have an incredible toolkit to build upon. And the absolute cornerstone of that modern toolkit is something you'll hear all the time:
ROS, the Robot Operating System. But wait, don't let the name fool you. It's not really an operating system like Windows or your Mac. It's much better to think of it as a robot's nervous system. It's the middleware that connects everything. It lets the sensor software talk to the planning software, which talks to the motor controllers, all in a standardized language. It hides the messy hardware details, so your code doesn't care which brand of laser scanner it's using. It just gets laser scan data.
Another absolutely critical tool in the box is simulation. This lets developers build and test their robots in a perfect virtual world before ever spending a dime on physical hardware. But this brings up a huge, famous challenge in robotics, the sim-to-real gap. You see, in the simulation, everything is perfect. A beautiful, clean digital world where physics behave, sensors are flawless, and crashing is free. But in the real world, oh, it's a mess. Physics are unpredictable, sensors are full of noise, and failures can be very, very expensive. A huge part of the game today is writing software that's tough enough to survive that jump from the perfect sim to messy reality. Okay, so when you start putting all these pieces together, the sensing, the planning, the acting, and these incredible tools that help us manage it all, you start to arrive at a really profound, kind of mind-bending idea about what intelligence even is for a robot. It's a concept called embodied intelligence, and the core idea is simple but powerful. A robot's mind isn't just some software floating in a void completely separate from its body. No way. Its intelligence is fundamentally shaped by its physical form, its hardware, and its constant back-and-forth interaction with the real world. The software and the hardware are deeply, completely intertwined. You can't truly understand one without the other. And this takes us to an even wilder place, a field called morphological computation. The idea here is that you can get the robot's body to solve problems for you so your software doesn't have to. Think about it. Instead of writing tons of complex code for a rigid gripper to pick up a weirdly shaped object, what if you just build a gripper out of a soft, squishy material? It will naturally conform to the object's shape without needing a single line of code to calculate grip forces. The body, the shape, the materials is literally doing the computation for you. So think about where we started. We started with this one simple line of code, and we've ended up here with this radical idea that a robot's physical body is a fundamental part of its intelligence. And that leaves us with a huge, fascinating question for the future. As we build more complex, more adaptable robots that can change their own shape, how in the world does our software need to evolve to keep up with that? How do you write the code for a mind when its body is no longer a fixed thing? Honestly, that is the next great frontier in robotics.